This is the CDFAM podcast with recordings from the CDFAM Computational Design Symposium held in New York City, October 29th to 30th, 2025.
Please bear with me. I'm Karthik. I'm a specialist engineer from Eaton. And I'll be talking about what you see here, metal to plastic conversion using AI, implicit CAD, and mesh-free simulation methodologies. I come from Eaton Research Lab, which is a central R&D solution for all of Eaton North America and part of global. But I don't think people are really aware of who Eaton is. I've not had the opportunity to network with most folks because I've been trying to save my voice for this talk. But I noticed something, Eaton is historically known as an electrical company or power management company. So it was interesting that I was waiting at the men's restroom this afternoon and there was this Eaton circuit breaker protection panel over there. So I got curious and I started snooping around the building, and the security guy was following me because I think I went to spots that I'm not supposed to be yet. I found a transformer, which is also made by Eaton. Whoever finds this Eaton transformer I don't have t-shirts to give away for the winner, but this building alone uses two of these Eaton products. But over the decade, Eaton has grown more than just an electronic or electrical company. It has been transition into a global power management company, but also an industry technology leader, mainly through targeted acquisitions. So we now have portfolios spanning beyond just electrical. We have solutions in technology, solutions in the aerospace sector, air filtrations for industrial applications, and e-mobility and vehicle applications as well. So that is Eaton in a nutshell. And like I said, I'm a specialist engineer from the R&D sector of the Eaton. So we kind of innovate on materials, manufacturing, and design, and cater to all these different business divisions within Eaton. What I'm interested right now, or at least my group is currently interested, which is I come from the materials and manufacturing group within the Eaton R&D center, is how do we use high performance polymers and composites as a metallic replacements for all of these different divisions. Aerospace, aerospace is a big proponent for weight reduction and cost reduction, so they are very interested in using high performance and high strength polymers for some of those applications. And we also have a lot of applications in the power electronics and data center cooling as well. So how do we make heat spreaders with thermally conductive polymer composites that's lightweight, that's also sustainable and more cost effective. And then you can see a bunch more electrical and automotive applications, engine housing casing, small interface materials, and sort of. So wherever we can think of deploying multifunctional polymer composites that can do just more than providing strength, but also can be electrically conductive, electrically insulative in some of the applications, but also has strength and thermal management solution capabilities as well. So that is where we're interested in high performance polymers for metallic replacements. But if you look across all these applications, the common challenge is how do we go from the traditional or existing legacy metallic components to the polymer counterpart without losing its functionality, manufacturability, and the structural integrity or the safety of these components. So that has been the underlying challenge, and a lot of metallic replacement is not a new topic. It's been over for many decades. But how can we innovate on the materials and manufacturing side and use digital technologies to accelerate the conversion process is really what I wanted to, the story is on that, and I wanted to share that with you folks. So the approach to metal to polymer conversion, it just boils down to how can we integrate materials, the physics of the material, the physics of the manufacturing, and the design aspect. How do we couple and tightly couple these three aspects together from a digital twin standpoint so that they can automate and iterate within themselves and give us the best outcome that is not only lightweight, but is also functional and manufacturable and meets the performance CTQ of whatever the operating conditions are. Traditionally metal design process, we have predefined manufacturability rules. We have deterministic FEA solvers that we can rely on. We have very known understanding of metallic properties, which are primarily isotropic in nature. So it is somewhat easier, but we can apply those same principles when we come to plastic or polymer composite lightweighting. So how do we capture, for instance, the materials anisotropy, especially if we use carbon fiber reinforced polymer composites, how do we capture the anisotropy or the direction dependent properties and that sort of physics into the design process? And then we do a lot of composite manufacturing. We do injection molding, we do robotic carbon fiber tape layer printing. So all of these have their own manufacturability, tooling or process inspired or induced manufacturing constraints. So how do we take that into the picture as well? And then coupling just these materials and manufacturing problems unlocks the design space, but also makes it complicated in exploring the design space and coming down to the best solution. So that is sort of the underlying or the hard problem to solve. And then on the simulation side, based on the performance constraints, we might have the design subjected to static load, dynamic load, impacts. How do we capture those multi-physics, multi-boundary conditions into the design iteration process? So those were some of the challenges that we were trying to address. And it all comes down to the design and simulation bottleneck. I kind of copied some of these slides from nTop and a bunch of other presentations, but the traditional CAD modeling and FEA loops are really slow, and they don't really enable rapid design iterations. Using traditional CAD packages, there are chances that the CAD updates might break down during the automated iteration process. There might be meshing failures during the simulation workflow, and then just the two things together add up a lot of simulation and computation time. And then organizationally, we have different experts working on different problems. So we have like a design engineer working on the design update. We have meshing specialist who is an expert on a specific software. And we have a simulation specialist. And we need to bring all of these folks together, and that adds a lot of lead time, integration of multiple expertise into the conversion process. So how do we mitigate this bottleneck from a design simulation, which is the iterative overload, and also organizationally, how do we consolidate these expertise into one unified conversion workflow is the challenge, and that is currently adding weeks and months of lead time to the conversion process, and that can go beyond, just from the R&D standpoint, taking to the production level, it can span over many months to years, getting that product out to the customers. So how do we cut down that lead time? How do we cut down the cost? Has always been the challenge with the traditional process. And that is where we really wanted to move more into implicit CAD and mesh-free as the backbone in accelerating and mitigating all of these issues right now with the traditional simulation approaches. So for starters, like Professor Ali mentioned, to be able to update the design iteratively without having failures is moving from traditional CAD B-rep representation to more of an implicit modeling. So we adopted nTop into a workflow for this lightweighting process. And then most importantly, which is kind of like the core essence of this topic, and Neel will speak more on the intact solution. So they offer mesh-free alternative to structural FEA analysis. And that alone has allowed us to save time from almost 40 minutes on this box. I'll talk about the box later, to cut down to 2 minutes in just simulation time. So being able to predict the same stress field at that time is a significant boost in our iteration process. And then the other thing, just wanted to spice things up. How do we go beyond the traditional sequential-based optimization, and how do we bring AI into the picture? So we were interested in maybe looking into algorithms like Bayesian optimization. How do you have Bayesian optimization use these tools through API, communicate with them, and train an AI model in the backend, and can that also accelerate the design conversion process from metal to plastics? And that just integrating these three tools has allowed us to go from weeks of design optimization to few hours. And I'll show you some use cases in leveraging these three tools together. So that's just on the design side of things. Like we have the Bayesian optimization that it starts with the design bounds. It speaks to nTop through nTop Automate through Python coding, so it can update the design during the iteration process. And then we call intact through PyIntact, which is another API through Python, so we can quickly evaluate that design in 2 minutes or so. But rather than going through a sequential optimization on the back end, we decided to take those data and teach an AI model, like something like a Gaussian process model, so that we can train an AI model, make some best guess on the design, and then check for feasibility, whether it's through strength or thermal conditions, that whatever the operating scenario is. If it doesn't meet, we go back, take the data, retrain itself, and then that just goes on in a continuous loop. This is not something new. I mean, none of what I'm presenting is new. It's just more of an application of different application and integration of different tools. But what was more interesting is how do we incorporate the material and manufacturing physics into this design exploration pipeline, and that is the left branch of things. For composite injection molding applications, now we started bringing in other commercially available tools into the picture. So for instance, we have Autodesk Moldflow, which also offers APIs. So we are able to bring in the geometry, and we are able to apply the specific injection molding constraints. So for instance, based on how we put the nozzle into the mold cavity, that will determine how the plastic flows into the cavity, and that will determine the fiber orientation and things like that. So to capture that and map it onto the structural geometry, we use Digimat's API as well. So they talk to each other, and it gets the mold flow results, and Digimat helps create the fiber mapping information, and we take that fiber mapping information and further map it through API with Intact's FE, meshless FE simulation. So now we can apply the boundary conditions while capturing for the material anisotropy within the geometry. And then how we bridge the two branches is we can now sort of predict the stress field point cloud map that is a resultant of coupling the manufacturing and material physics on the back end. And nTop has this field-driven design approach, so we are able to take that stress field and link it to the AI-driven pipeline. So now we don't have middlemen speaking on where to add or remove material in the design optimization process. So we have this field-driven design dictating and telling nTop and the AI-driven pipeline on where to remove material, where to add material, and then that just feeds the iteration on its own. So that's just kind of the workflow that we built that allowed us to go from weeks to a few hours in the design conversion process. So one slide on one of the applications. So this is a box that houses some electrical components. So we need it to be electrically insulated, but also strong enough to contain any gas leaks from those components. So it needs to be explosion-proof sealing. Explosion-proof, not in the boom kind of explosion, just to contain the gas leakages from the components. So how do we go from a box looking to a slightly cooler box that is lighter but also meets the material and the manufacturability and the safety requirements of that, and we were able to achieve that in a few hours. And that's just one single iteration, but the integration of the mesh-free and the implicit CAD allowed us to rerun this many times. So we have to speak with our external manufacturing supplier who had a lot of issues. So we go back, we add those things, and we can come up with a new design in less than 2 hours. And we were able to redo the design until we met both the customer requirements and the manufacturability requirements as well, which wouldn't have been possible. That would have taken us like 6 to 8 months. We were able to get down to like 1 to 2 months with this entire workflow, and now this is being produced right now externally with our manufacturing supplier. And yeah, like I said, it is just a box. I remember when we first showed this to Duan, he was like, "Oh, this is all cool, guys, but it's a box. Like, why do you need such a sophisticated AI, implicit CAD, mesh-free, and all of this stuff?" I agree. Like I said, the win for us is being able to cut down the development time from 6 months to less than 2 months. That is a huge win. We saved a lot on cost and the time, and we're able to get to manufacturability quicker than we were able to before. But then most importantly, we were able to build this workflow, put together a more robust workflow of integrating implicit CAD, mesh-free analysis, and the AI as a backbone that learns from its solution and iterates through the design optimization. And now we are able to apply it to more complicated and expensive problems out there within Eaton. So this was just sort of like a proof of concept within our Eaton Research Lab, and now we have the buy-in from our leadership on deploying this tool on other applications as well. For example, now we use this lightweighting, or this is not really a metal to plastic conversion workflow. It's a lightweighting problem. It's metallic 3D printing, but how do we use mesh-free and implicit CAD to lightweight this aerospace accumulator? So we have, this vessel is going to be 3D printed using robotic carbon fiber AFP process, but then the end cap or the enclosure, they have many names for that, but that needs to be tightly put into the vessel, and we wanted to 3D print that and explore opportunities for lightweighting. So we were able to use nTop and Intact integration, the API integration, to within few hours we were able to go from that design to the one on the right, which is 45% lighter but also 20% stiffer. And now we are using Power Bit Fusion to 3D print that as we speak. And then there are other ongoing use cases. I already talked about this. We have, another thing, Eaton Research Lab works with a lot of government funded programs. So we work with DOD, ARL, and Engineering Research Development Center. So that one is a 9-foot long sector gear that they use that to open water dams. So the Engineering Research and Development Center, they came back to us and they're like, hey, we want to 3D print that using DD process, but we want to cut down the cost on that. So we're using the same approach to lightweight this for them. Then we have like cold spray, thermal management. So how do we come with the best spray pattern that uses the least material but maximizes the thermal dissipation? It's the same problem. Instead of structural, we're solving for thermal, so we're able to deploy the nTop and intact workflow here and coming up with the best pattern. And then there are ongoing interest in how do we do thermoset to thermoplastic conversions as well. We have some more time. I want to give the presentation to Neel, who will speak a little bit more on, I can skip the takeaway and insights on the intact.
Thank you, Karthik. So basically, as Karthik showed, what a simulation which is behind the scene, available on demand and reliable can do to your design process. I just wanted to talk a little bit about intact simulation, the simulation platform that's what's behind that. So he already touched upon all the problems that he was facing in meshing, cleanup, geometry, and all these problems essentially creates this big barrier to automation for traditional fundamental analysis and makes it not automatable. And the kind of workflows we want to build today will not work if your simulation is not fully automatable and reliable behind the scenes, right? So you want to do large-scale design exploration, optimization at scale, building digital threads where new data comes in and your thread just updates itself. Or now we have better and better physics models. So which depends on a lot of data, simulation data. So how do we generate these data reliably to train these models? So our approach to solving this automation problem is essentially separating geometry from the simulation space or the grid or the elements, whatever you want to call it. So instead of trying to mesh the geometry, we immerse our geometry in this simulation space, and at runtime we fuse the two and compute all the important physics quantities you need to be able to solve. And this has two very important implications for us. On the left side, since we're not meshing the geometry anymore, so basically you can just feed it any geometry where you can compute its volume, we can simulate it, right? And on the right side, because this grid space is essentially classical finite element analysis, so any CA solver that you already use is easily pluggable to this. And the implications of having this type of meshing-free simulation is that now you're able to analyze very complex models, like these implicit lattices and rib structures, some from nTop again, very easily, which will take days to mesh and clean up and be able to simulate. And not only that, now you can easily mix and match representations. Sometimes you have BREP and implicit inside lattices. You can do that. And sometimes there are non-traditional representations which represent a valid volume, but to be able to simulate that, you'll have to create a surface mesh of this CT scan data. But with meshless, you can just do the simulation right away on the representation. We are already available in many of the computational design platforms out there because our goal is to be where you are. So we are in Rhino, directly simulating implicits in nTop, Synera, the process automation, so we are available natively in that platform as well. CDS uses in their design pipelines, and we're also on the cloud and have integration with Onshape. And finally, really excited to talk a little bit about PyIntact. So we released earlier this year PyIntact, which is essentially a very native cross-platform Python API for our meshless simulation. And what this does is now you can basically programmatically set up simulations. I think the animation did not run. Yeah. You very easily set up these kind of simulations, set up once and just throw hundreds and thousands of designs at it and it'll simulate it for you. You just leave your computer overnight. We also have basically level up optimization built in, and we provide you with the sensitivities data, the gradients, whatever you need to drive your design decisions. All of those are available natively inside Python. Very quickly, you can run thousands of simulations to do your design space exploration. And just to stress, like, it's very native to Python, meaning you can use all your existing modules, ML tools, and all our data types are in memory, so you're not doing some hacky way of calling external applications and doing file-based in-out reading, writing. It's all natively in Python. And again, available both on Linux and Windows and can be easily deployed on cluster. And with that, I'll wrap up. So Intact is still young, but we have great leading partners now who are working with us and getting great success in different types of application areas. You saw they are seeing quite a bit speed up in their design iteration, being able to do automated design of experiments at scale, from concept to validation, and while staying in their design workflows. So with that, I'll wrap up this session, and we can all head for coffee.
To see the full recording of this and previous presentations, as well as information about future CDFAM events, visit cdfam.com.